So let's begin. I'm Dmitry Chuyko. I work at a company named Bellsoft. Today it will be one more OpenJDK talk, probably more generic and also focused to the work that we do at Bellsoft, but not limited to it. That's me. I work at Bellsoft. We have small OpenJDK team, and previously we all worked at Oracle. I worked at performance team, so that's what I'm continuing to do now. And Bellsoft is a service company. We do ARM stuff, and we also release our own distribution of OpenJDK called Liberec. It's a DCK verified bundle of OpenJDK, which is important, I believe. I'll mention it today. So we'll discuss contributions in OpenJDK. I especially remember well what happened for past year, because it was not so long ago, and how the process goes, and what do we struggle with, and how it happens. So interesting statistics, which is, of course, always tricky, because you cannot compare one thing to another directly. Which is, what's interesting on this picture, it's the statistics of contributions to OpenJDK for some time period, like 1 year till this August. What's interesting is how many companies contribute to OpenJDK, and particularly we have a strong community in ARM space. This was really warmly accepted on JDK committers workshop this year, and it is good. And the other flashback here is new release cadence, because this is statistics for just 1 year, but what happened for a few past years? JDK 8 was released in 2014, after a few years of work, and then 3 years later JDK 9 was released, and just in a year it was 10, it was last year, and we already participated in that release, and now it starts speeding up, and we are to the new JDK cadence, which is 6 months. So 6 months of development, 6 months for support from Oracle engineers in open. But it should be more long-lasting support in general from other companies and maybe from Oracle too, for long-term releases, long-term support releases. So for this past year, it was JDK 11, which will be released this fall. It's already in release candidate phase. Yeah. So if we talk about applications and some platform, what's typical? I don't know the clear answer. I have some assumptions, some experience. Of course, Java had long embedded story, so different flavors of Java, but it was on 32-bit ARM. For now, we have more recent, more powerful so-called platform versions, but you still have choice sometimes which one to use. For example, on Raspberry, you can have both ISA versions, anything. And you have typical assumptions, and I do, about what applications we can find on such devices. Like tiny user experience devices, probably GUIs. You can press some button, interactive touch screen, anything. Or you can collect data from sensors and send them to the cloud, for example. And in the cloud, you can have some backend accepting those data or processing them as a big sets of data, like big data or databases, etc. So that kinds of workloads are different. And it's not always clear how these tasks are mapped to architectures, right? So you can have like a 64 device which does a GUI job, and it's fine. Or you can make a gateway on a 32-bit, right? So we have some preferences and some story, because we worked with KVM. So I believe what we suppose here is that, well, 64-bit architecture is more suitable for backend applications, for big data, of course. And again, we should recall the dates. So at the time that we started after JDK 9 and working on JDK 10 and 11. Most recent hardware was not released yet. And yeah, hopefully the ThunderX was stable at that time, but still the microarchitectures change, and well, we worked with what we have. Now we have a better option. From the other hand, we have some typical devices, so-called like Raspberry, and we make our own Java distribution just to be visible in the community. We really love this as a Playmate project, and the distribution is itself a TCK verified Java. It has some specific modules in case of like Raspberry, to work with GUI, to work with device I/O. So that are things that distinguish one Java from another, some additional sources. And we also released that even for AR64 and even for Intel, and maybe for Windows. Just stay tuned. And basically, then you, for example, get Raspberry. What do you get out of the box? Or what do you get out of the repos? You get JDK 8, which is definitely not the best choice from my perspective, because, as I said, it was released in 2014. And it's, well, JDK 11 is on the way. It will be new LTS release. JDK support will last for maybe for long, but that's not something that developers want. So as I said, yeah, we have Liberec. It's all described on some pages like release notes. It's open sourced by the general licenses, I believe, like OpenJDK, JPL2, and not viral in case of Java. It works with some additional sources. And for JDK 9, you got bonuses like ability to split your application to cut off unnecessary dependencies inside JDK to minimize your deployment. And we went even further because, in general, OpenJDK has notions of client and minimal VM, which are smaller subsets of the entire runtime. Like you can strip off server compiler, you can strip off most garbage collectors you don't need on embedded devices, and to get your minimized, very dense runtime. And with Jigsaw, you can strip off the part of dependencies from the core library that you don't need again. That's important sometimes. And to support that, it required some work in OpenJDK space because some things were just like broken. That's essential. So when this started to work, we immediately started with 64-bit ARM. And initially, we were new to the architecture. So we had not just a perspective of JDK developer, but also a perspective of the user. It was good that they had the hardware because at the times when it started, JDK developers sometimes had no real hardware to test on. So from a consumer perspective, you can buy something from one more vendor, which is not Intel, not Oracle, or not HP, someone else who can offer probably cheaper solution, more power effective, and as performant as your current option, maybe. So from a JDK perspective, another ISA is another ISA. It requires a lot of work to realize what's the difference, what are key points of changing things. Maybe sometimes it requires generic fixes to allow different behavior in certain places. And it is so for all parts of OpenJDK and related projects, like we know for garbage collection, for Graal. That's true. Yeah. And when someone chooses an option to deploy his or her application, like it may be a web server or something, what good is Java for here is that you can easily transfer your already made application from another platform. It's just probably a jar or some other kind of archive. And you just pick another JVM, you may pick another platform. It just works. It must work because it's Java. But will you do it as a customer? Only if it works fine, if it satisfies your SLA agreements, your quality tests, etc. And then we talk about pricing and some competition. Yeah, the performance should be very good. And we work in this area. As I said, we target primarily KVM cores, but we also really carefully test on Cortex cores. And we have our own small lab of machines, maybe not as big as some of you have, but we do. We also use public clouds, like Packet, which offers bare metal servers. And we have vendor machines for us. So that's pretty straightforward. So what is Java in general? It's an ecosystem, not just, well, formally, it's just two specifications, right? But at this time, we have implementations, different ones. It may be OpenJDK. There are others. Like, for example, IBM-based, J9-based versions of Java. Or it may be Graal VM, Graal images. For now, it's Linux, but things may change. And we are working in hotspot space, in OpenJDK hotspot, and it has its own caveats. For example, it has ports. What support is all specific, for example, CPU-specific stuff related to one architecture in all areas, like runtime, garbage collection, JIT compilation, interpretation, everything. It may be separated and implemented in different ways. And it is implemented in different ways. For ARM, for example, there is unified port for ARM32 and ARM64 from Oracle, open source now. There is a special port for ARM32 from Azul, I believe, existing in a separate tree. And there is AR64 port in mainline. And there is also Graal, which is a standalone one because it's not a part of OpenJDK as a project, but it is a part of OpenJDK of Hotspot as a source. That's kind of funny, but we leave this way of doing things. It's being imported and bundled with OpenJDK. So as I mentioned, for 64-bit ARM, there are currently 2 ports in mainline. The process is going the way that the first port will be decommissioned for ARM64. It will stay there for ARM32. But we still have to support it because someone may build OpenJDK, build that port and use it. For example, someone who wants to try, like, I don't know, Java 11 with JDK 8 flavor. Like, it will be the same port, but with some new features at least. So we also spent some resources of keeping it clean. So this is JDK 8. If you look for bundles with this port, that will be JDK 8. And if you look for JDK 8, you'll find bundles with this port. It won't be continued. But at the time we started our work, the situation was like there are 2 ports. They both exist. They both open sourced. They are both in mainline. And that's what we have now. So we have to compare, we have to choose, and we have to improve something. The general notion already was that AR64-bit port will be the mainline. So that was the consensus. But the additional port is a source of interesting findings, potentially. So we analyzed what we had in that port, what we had at new port, in our compilers, what can they improve. We've done some analysis, we made few tables, big ones. One of low-hanging fruits was improvement of intrinsics. So if we want to make better OpenJDK in terms of performance, we can improve intrinsics. We also had an option to test our work on the real hardware to verify the performance. And we stand it on the shoulders of giants. So a lot of companies contributed to the common good. So at least we had stable hardware, which was not true for not so long time ago, especially for multi-threaded applications. Well, things may be crashing. And we had working operating systems, pretty stable, modern kernels with modern features, with hardware counter support. So then you do performance analysis of your code. You typically need to understand what happens in CPU if it's CPU bound. So you need performance counters, and you need to, well, realize what's hot in terms of events happening in CPU. Then you run your application, your workload. And we had some examples of really good work already have been done in OpenJDK in other areas. That's really helpful. So for not a long time, we went to the situation with many things available. Like for examples, Cavium ships its hardware and clusters are built from that. That's a very good situation. I was blown up by all the details of PostCake supercomputer, just because it's lots of ARM cores, SV, super interconnect. I know that's really mind-blowing. And where's Java in this space? Of course, it's possible to see it as a big data processing, as databases everywhere in clusters. Of course, in management. If you run even some super handwritten assembly and C optimized native code on your supercomputers, you probably manage all the stuff, how work goes. And it's a good space for Java there. There are solutions for managing, like containers, resources, all the things. Of course, it all may be deployed in some cloud. It should be transparent, probably to the user, which hardware is used. But again, Java is wanted here because it allows to hide even more underlying details. So important to have everything working and to have good performance. And there are a lot of applications we all know, like works on ARM. A lot of stuff is Java containing stuff. A lot of other things, but a lot of Java. So we came to introducing a Java Enhancement Proposal for improvement of intrinsics as some general formula of doing things, because that was the visible result of our work in OpenJDK for this period. It's a joint job of Bellsoft and Cavium. You can find it in OpenJDK in public space. There's an obvious motivation of improving scores, at least in micro benchmarks, but in general also. We noticed that some things were missing, and that were important parts from our perspective, and some things to improve on particular hardware, but hopefully in general. So I don't know if it's visible fine. I would say this picture, the really good results, speed ups, etc. Besides of all this, from my perspective, three major parts in this short list of successes. First is a set of operations, bulk operations with data chunks. Like, for example, calculating CRC or copying or comparing memory. That are important tasks. Related group of strings operation, where you can compare against strings, find something. Strings are also represented as memory chunks in the end, but some details are different, like you have to take into account the string encoding, etc. So some string specific is present, and the typical string lengths are a bit different from, well, typical array lengths for some other tasks. And there is one more group which looks not related to data chunk processing. It's a group of math functions, which we continue to work on. That's a scalar math functions calculation, But the interesting future work here is the work that's similar to work that Intel does, the calculation of same things in parallel. I mean, like vector processing. So then you calculate many sinus functions at row, which is really loosely coupled with vector API work. So probably we'll see some interesting results here in future. So not just for scalar calculations, but different thing for vector calculations. And yeah, thanks for joint work on strings, string intrinsics. Yeah, as negatives was an interesting first experience of throwing into the OpenJDK space of AR64. And it was a success. That's really a good example of doing things together, maybe not very rapidly, but with a high quality. For quality, it's hard to do complex things. So we still continue to fix issues in math functions. This is a really complex area because it includes heavy algorithmic optimizations, not just, well, you know, microarchitecture tricks. And other areas are more to, well, good crafting assembly code, handcrafting it. And we double check the performance in micro benchmarks on different microarchitectures. And also we try to find something bigger to check our modifications. I'll show one example here today, and we'll discuss probably it a bit later. So what we use for evaluation. We need to measure some scores. So you need benchmarks. For micro benchmarking, we worked with Java, and we also worked with CPUs. So sometimes we have to make native benchmarks, not surprisingly, to check some patterns of assembly code well, directly, not involving any Java stuff. And sometimes we are fine just with Java benchmarks. And as a standard, we use Java Micro Benchmarking Harness, JMH. We also use widely accessible benchmarks, industry ones like spec benchmarks, and some bigger workloads like Hadoop benchmarks, not just Terrasol, but also others. What we like to do is to work with fixed bugs. So we don't want to optimize what's already have been optimized in mainline. So we run latest software on latest JDK. We'll see an example here today. And then you work with something bigger than a micro benchmark, or even with a micro benchmark, you sometimes need to profile, and it's better to profile. So we need profilers. And we briefly discussed yesterday, what do we have here as an options? Of course, it's better to be based on low-level things we have. So we wish to collect hardware events using system mechanisms like perf or BPF as an analysis, well, aggregation stuff. Java has its own specific. It's not just a program, but it's a program consisting of many parts. So it has its own statically compiled runtime, and even not statically these days. It has JIT compilers. And in the end, and it also has offline compiler. And in the end, and it has also interpreter. So your code, then you write some Java method that's for you as a developer is just a method, having a name, having a body, and all the stuff. It can end up executing in different states, in really different states. So there may be multiple versions of this method compiled with different JIT compilers. some profiling, it can be executed in interpreter, so you won't see the code of your method. You may see multiple codes, some entry points, many different things. So for using an attribution of, for using profilers and attributing your methods, you need some clues, some hints for system tools to clue that pieces of profiling information into some good information about your method. So I'm describing a bit for so long to say that there are special profilers for Java. You can profile it in a very simple way from user perspective, just looking at Java stacks. You can, in a standard way, ask Java VM periodically and make stack sampling to get the notion of what's the virtual machine relatively is doing in some moments. There will be a strong bias in the data, and the sampling won't be very frequent. So you'll be getting the approximate profile of your application. There are other means. There is an internal API in Hotspot called async.callTrace, which gives you a better sampling options. And it can be combined with perf events. It allows, for example, not to use any agent with your application that will tell perf about Java methods. So this approach lowers the overhead of profiling, which is really important. Then you need to look at some tiny things. And remember, we worked with different versions of Java, even for the same, for example, Java version on the same microarchitecture. Boom. But we don't want to do so. As I said, we want to stick to a newer version, so we stick to one port, but also made some work for JDK 8. So we basically like two profilers. One is called async profiler that does exactly what I said. It combines perf events, even like cache misses, for example, or page faults, and basically, of course, CPU spent, and Java information, what methods were executed. And the other thing is a built-in mechanism released. It's been released now in JDK 11 as an open source. It has been released for x86 in Java 8, and it's called Java Flight Recorder. And there's a tool for working with such information, which is called Java Mission Control. So Java Flight Recorder records internal events from the virtual machine from some places in an efficient way with low overhead in some chunks that can be transferred over the network or stored into disk. So the benefit of Flight Recorder is ability to use mission control and to use also an official API for doing stuff in a cross-platform way. So we participated in fixing both for the platform, for support, and we wished to use them ourselves. That was an important motivation for doing this. So as I said, async profiler, it's an open source tool. If you need some fixes, please do them. It's free, it's up to date, so it works. It works with recent version of Java, which will be Java 11. And also it works from 9 up to 11, and also works with 12. So here are fixes we made, some general support and some specific CPU-specific support for T99 for Thunder X2. SetBill here is that this tool won't work with JDK 8. You'll need something else. Also, we discovered that currently it doesn't work if you involve AUT code. So then you step on AUT frame, your hotspot crashes. That's just something to fix. So let's look how we improved at least something and how we measured that using the tools. As an example, let's look at CRC calculation. Quite an essential task. In Java, it's declared in the standard API as an implementation of Java checksum interface. There are, for example, 2 different CRC checksums available for quite a long time. And there are different ways of implementation for such things in OpenJDK. So you can stick to Java-based implementation. That's possible. You can have class library where you have normal class, and it can contain Java code, and it will be compiled or not compiled or just executed as any other Java code. You can also have an intrinsic, some native code that will replace, in some cases, your Java method instantly. So we won't need, for example, to JIT compile it to get better performance. You'll just glue some piece of native code into a hot spot of your application, or make a call to a stub. So this native replacement can be written, for example, in C, and there is an optimized statically linked library called ifdlibm. Or it can be implemented in C or macro assembly inside the hotspot, in the runtime part or compiler part. So there are different options. Where we started our work with this one, in AR64 port, there already was very good implementation from the Naro. So we had to look at this from multiple sides. Even there, few implementations were available, and there are possible options. There are algorithmic options and instruction set options. So at least you have subsets of instructions like neon instructions, specialized CRC instructions, what we consider available but not always. So how does it work and where it's applicable? As I said, it's a widely well-known tasks of checksum calculations, and it's widely used. Of course, it's an integrity check thing, and if you look at many major products and technologies, you'll see, well, wide adoption of this. But how it's implemented, how it's used, how it's calculated. Let's, for example, look at HDFS and Hadoop Core. We'll see that checksums are typically calculated on block size of 0.5 kilobyte. That's the default. And it's really rarely modified. There's already a bigger chunk from which we took pieces and calculate a checksum for each piece. There is some default checksum, which is also important. And it's important to know which default to offer on the platform. Because this default, of course, was selected for Intel, which may be not true for any ARM microarchitecture. It's an option. And surprisingly, a lot of such products and technologies have their own implementation and with a long history of modifications. Like, we are going to implement some checksumming. OK, here's the code snippet from somewhere. It works. OK. Then after a few months, oh, it doesn't work. We'll fix it. And a few months ago, oh, it doesn't work well. We'll improve it. And then again, it just contains some error. and again and again. Of course, in JDK code, there is also such history, but it's the one and major place of having such functions. So it's better, probably, to use class library 1. But will it be the best choice? So if you look again at Hadoop Common, it's an interesting example of technology because it's currently really heavily tied to JDK 8. I believe it will last be compilable on 8 for ages. And it is true for other similar products. So we have to deal with this in any case. It has its own pure Java implementations. And if you remember, not all checksums are available at 8. Now, that's it. But in a good case, it uses, for example, for just CRC32, not C, built-in classes. And it also has an implementation in native library, which may be loaded in case it presents. Thank you, Linaro, for the native library implementation, which is also good. It also introduces a nice trick of independent calculations of multiple blocks. So then you check your checksums. You can independently load pieces of data to have better pipelining and less data dependencies, so which is very good. But if a user downloads like Hadoop distribution from the official site, what will he get? He'll get native library for x86, which won't load, and he'll fall to Java implementation. The only notice is there will be an output of in standard output saying that you're not using native library, that's okay. But that's actually sad, because the performance will be bad. So we benchmarked different versions for this intrinsic in OpenJDK. We tried algorithmic optimizations. The funny ones, like the ones similar to what Intel does, like recombinating parts of checksum for a larger block. And it's funny, it's still slower than the one we got. We used JMH and all the tools related to JMH, like perf profilers. So in JMH, you can easily write Java benchmarks like this. And you have like basically benchmark method. And all the other stuff Harness will do for you. It will trick JIT compilers in necessary places, etc. So you basically see what's being benchmarked. Here it's really simple. You just create a buffer, and then you test the method you want to test. So in this benchmark, we initially applied we initially made a check about the default implementation on the interesting platforms. And there are options of implementing this algorithm. So specialized instruction is the best option, but not the only. That's a mandatory check. And you see how good this best option is. We changed nothing for so long, right? We're just checking. So now what about optimization? Our initial assumption about all that operations, the data blocks, was we'll put prefetching everywhere, and it will help. It's so good to have different kinds of prefetching on ARM. It's so rich. It really helps somewhere. For example, you see that if you put prefetching, it helps, well, here. But does it make sense? Not at all. Because you have to be in a situation, then you calculate checksum of a single multi-megabytes block. Maybe sometimes you are. But do you really need to optimize it that way and lose the performance in really important cases? Like losing 4% in the middle of this plot. So it's a speed of checksum calculation, higher is better, and it's a size of block. In bytes and megabytes, it's not so important. And the speed up observed was only for one microarchitecture which doesn't have hardware prefetcher. Surprise. Not really. Maybe the benchmark is wrong. So we made another ones. Like for example, we can walk some larger buffer, make no copying, and update the checksum. Does it make sense? Well, not really. It can be very good improved, but that's the wrong benchmark because it makes no sense. And the sense here, if you divide the larger buffer into smaller chunks, then you probably do copying, and then you're in the situation of the first benchmark. So we made additional benchmarks for copying situations anyway. So what we started with was a very good and nice looking loop like this. In the end, we modified it just slightly after doing many experiments. Not changing the algorithm, but just changing the, well, details in the instruction orchestration. And it surprisingly gave good results. So only, well, less smart microarchitectures, we got good speed up immediately. On more smart microarchitectures, the speed up observed is, well, you fully utilize your CPU, but anyway. And again, we have to keep in mind the block size. But that's not the only part. Then you have some native code. It works only in certain scenarios. And there is a scenario for big data, for example, when your container lives not for so long, for like seconds, and the warm-up is really important there. You have to get instant performance of such functions. So we also made fixes to like C1 interpreter to use all the same code. It's also good for correctness, but again, this is not enough because OpenJDK has new compiler written in Java called Graal, and it has to use the same optimizations. So the goal nowadays, then you optimize something, you have to optimize it in one more place in Graal. That's what we also do for string intrinsics. And well, I see really good work in Graal right now. And Graal is available for x86 from Java 9 as an experimental option. It's now available there just as an option in 11. And in 11, it will be there for AR64, and sometimes it even works, which is really impressive. Also as a result of AOT work being done. So some results we got. We got an improvement released in Hadoop, not in Java, an improvement released in Java. So we can combine them, compare the native library with pure Java implementation from Hadoop, and then big benchmarks, like for example in TerraSort, optionally using some harnesses like HighBench. And we do it on the most recent Hadoop version because we change it. The most recent JDK version, so we have to modify HighBench to run it all, and we do some yarn setup. And we use profilers even on systems that are not CPU bound because we can get some meaningful result there. There are some tricks of using profilers like async profiler. Some brief information is here. And then you get some flame graphs like this, for example. Do you see any difference than patches applied? I don't. But you can zoom and to study it more carefully. So you can see the interesting method here in profiles and to find stacks that use it. and even to see difference in samples and the CPU spent there. There is a speculative estimate of improvement and the actual measurements that prove that it exists. So then they also used, of course, the benchmarks that change technology offers us. So Hadoop Commons has its own benchmarking stuff, and we compared it on different platforms, including x86, because we change common part. This is also so for any optimizations made in common part, for example, in OpenJDK. You have to look at x86, and backwards, you have to check x86 improvements on our platform. Sometimes the result is interesting, like last week or 2 weeks ago, there was an improvement for crypto stuff for x86, which shown the exactly same regression on ARM. And that seems to be a typical situation, unfortunately. So I have to deal with it. So I made some comparisons, maybe not so interesting. So what's about flight recorder? Yes, we also can use it with even such technologies as Hadoop. And we can see basically the same things. Like then you look at the bigger perspective, then you look at the processes perspective for JVM processes. You see that there are processes with their lifetime and consumed CPU. They are mostly cold, but the entire machine is pretty good utilized. So you see, maybe not so well. The CPU utilization goes like up to 80% at some points. But the lower part here, not so clearly visible, is the consumption of CPU for this particular process, which we track. So flight recorder here records information for this process, the get information just from one process, and also for the entire machine. So that's the overall picture. And we can have multi-node things going on. So if you look at Node Manager, we'll see some gray stripes here that correlate to something that happens and is managed by that Node Manager. Then we look at threads. And if you look at data node, then we'll probably notice data transfers, right? Even when we look at a single process, but the interior mechanism of things going on reflects what happens with all the processes in the cluster. And again, if you look at just one, for example, MapReduce process, we'll get basically the same information about hot methods, but not the details, and it's a bit shifted. Like here we see that it does sorting. It's thorough sort, so that's normal. So what's interesting in JDK 10 and 9, probably you heard Stuart's talk. I won't overlap too much here. String intrinsics allow to complete compact string support, which is really important for business applications because they all work with strings. It may be JSON, XML, or anything strings. AUT support was implemented, which brought GRAL on the platform. And also, it seems to help for application startup if you use it carefully. For example, you cannot AUT compile currently the entire Java.base module, and that's not right for the R64. But then you compile hot methods for Hadoop, for example. You can see like 7 to 8% workload speed up in some cases, which is really a good number. That's what AUT is for. AppCDS, Application Class Data Sharing. It's also a good feature we participated in porting. It doesn't help for workload times, but it can help to save your footprint. Maybe a bit for things like MapReduce, but for other tasks like web servers, this may be really critical. And it also helps for startup there. Some bigger things. We know the port is now competitive for some time. If you get the latest Java magazine, there's an article mentioning those numbers. We tried some dummy setups. For example, this is SpecJBB composite. And the minimal tuning was made for both machines. We took Intel machine that Cavium competes to officially and just compared scores. So you see both critical and max operations are higher, which is better. And that's JDK 11. And also in SpecJVM, the result is about the same. So you see the lines. Nothing, not so much to comment. So we are continuing our work with intrinsics and other stuff and doing new things. Particularly at Bellsoft, we started value types work, which should be also good for performance and in stuff like Cassandra, for example. And we know that other things are going on, like, again, ZGC work, which is a great perspective for having a low latency collector, one more one. And we still have stability issues. We continue in Java 12 to improve intrinsics, which is work that's not finished. And vector API is on the go, because it also opens many perspectives. But that's not the only Panama part, because I think layouts and FFI is also important. So, as I said, our perspective is to be focused on applications, to carefully test all the changes with applications, to test optimizations, verify it with profiling, and micro-benchmarking. So let's continue to contribute not only to OpenJDK, but also surrounding technologies like profiling and frameworks based on OpenJDK. Thank you. Do we have some time for questions? Yeah.
So the JFR, for your experience, it's a stable tool for profile?
Yeah, but it may be, the question is this JFR scalable and if it's a good tool for production? It's designed to be a tool for production, but it's sometimes not easy to use it when you have many JVMs. So that's a good challenge, what to profile. That's true not only for JFR, but JFR probably is slightly simpler to use than, for example, async profiler in this case. Yeah.
I have one more question. So the app CDS, are you specifically focusing on just app CDS or CDS in general?
So there are two CDS parts. General class data sharing, that's for system classes, and that's a separate archive. There is a JEP for JDK 12 or just an enhancement to create it by default in some certain cases. And there is a class data sharing for applications, app CDS. Then you can reuse loaded class data and decoded class data information for your application classes, loaded with certain class loaders, and it works. Basically, we checked benchmarks similar to x86. I used to be involved in that project, so we kind of realized what happens. And the speedups are similar, so it works very well. it can help you to save a lot of footprint. Then you start many similar things. Okay. Yep. No more questions? Thanks again. I think we'll have some offline discussion.